Hello guys, welcome to the video. So in this video, I would like to, give you a very, I think it's unique. I'm not really sure because I haven't found exactly this explanation, this analogy being drawn out before. But I'm not saying this is unique in the sense that, well, you may find it in some textbooks or I'm pretty sure you'll find it somewhere on the internet. But anyway, I'm not claiming this to be my idea, but I want to discuss a very good way to think about ergodicity. So maybe you know what ergodicity means. If you don't, I would give you a very simple idea. But before we start, just for the general audience, this video is about a very fundamental law of statistical physics or even statistics in general that I'll be trying to give you a visual intuition without going into equations. That's why I'm not screen sharing or showing you any equations and stuff like that, because I would try to it's really very intuitive. If you just follow what I'm saying very intently, you don't really need to, because this is not a lecture, this is not a class. So yeah, there is one point where I would talk about a distribution, so you have to do a little bit of visualization, but it's not really that complicated, I think. So well, let's start. What is ergodicity or the ergodic hypothesis? It's a very fundamental assumption in statistical physics, and it simply means that, well, there are two definitions, and like of course both are equivalent definitions because it's the same scientific principle. We cannot have two fundamentally different definitions of the same hypothesis or same principle, whatever you want to call it. But one of them is a bit easier to understand. I'll go with this one first. It says that the time average is equal to the ensemble average. Now, I know that didn't make sense to some of you who are not familiar with the language of statistical physics, but the idea is really simple. Let's say you have a system. It has some microscopic property as well as some macroscopic property. So let us say for a moment the system is a hotel room, a room in a hotel, and as a receptionist of the hotel, you have the information that whether the room is currently occupied or whether it's empty, whether it's currently occupied by some guest or whether it's empty. So that is, you can think of it, just this is just an example, just an analogy, by the way. So you can think of it that that room is kind of like the macro state, the macroscopic system. So empty or occupied are the macro states. So the room can either be empty when it's in the empty macro state or occupied when it's in the occupied macro state. That is the macro state. But if you want to go microscopic, if you want to know all the details, then there can be, for the same macro state, there can be more than one possibility. For instance, let us say the macro state is occupied, but then if there is a single individual living in that room, like the guest is just one person, then also it's occupied. If it's 2%, then also it's occupied. If it's 3%, then also it's occupied. If the two persons are like husband and wife, like a couple, then also it's occupied. If the 2% are just like friends, then also it's occupied. So all of these correspond to the same macro state, which is occupied, but they are different microscopic states. So the micro states are different. So this was a simple example to give you the intuition, but in real systems, of course, in statistical physics comes into play when we talk about large systems. So systems with a large number of particles. Interacting particles, ideally yes, but that makes the math more complicated. So in many scenarios, especially in the for equilibrium cases, we assume that the particles are not effectively not interacting, so they're independent particles. So the statistics of independent random variables is much more simpler, of course. But that's not the point. You need a large number of particles, and that's when statistical physics comes in. But now that you have an understanding of macrostates and microstates, let's talk about ergodic, I mean, the time average and ensemble average. So let's say you have a box of gas, like a box in which there are, gas means like there are billions of millions of gas particles, like 10 to the power 23 is 1 mole. So you have an idea, like large number of gas particles, atoms, or gas molecules colliding around in the box, right? So what is your macro state? You decide. Let's say for instance your macro state is energy. So that means you have fixed the energy of the box. That means you are not adding any energy from the outside. You are not taking away any energy from the box. The box is just kept in an isolated environment. You are not changing temperature. You are not adding or removing gas particles. You are not doing any of that. You are not compressing or expanding the box. Just an isolated box. It's not having any kind of exchange of energy or information with the surroundings. So that means the energy is constant. And you say, okay, currently the energy of the box is, let's say, this much. So I fix this is the macro state. Just like in that case, you fix that the macro state is occupied. Okay, so currently the room is occupied, that is fixed. Now in how many different ways can it be occupied? It can be one guest, two guests, three guests, and so on and so forth. Similarly, for that same value of energy, same value of that energy in the box of gas, there are many possible configurations of the particles, the gas particles, for which you can get this same value of energy. For the same macro state, there are many number of microstates. By the way, that's what entropy is. Entropy we usually say is a measure of disorder, which is a very, in a way, it's a bit misleading. definition of entropy. But yeah, if at high school level or at a very young level, we often say this just to simplify. The entropy is disorder. What entropy actually is the number of microstates for a given macrostate. That's it. So for the same macrostate which you have fixed, if you have many possible arrangements that correspond to the same macrostate, then the entropy of the system is really large. And yeah, in a way it's disordered because there are many ways to get there, and like many possible arrangements, it's not perfectly ordered. Because if it's perfectly ordered, there are only a few ways to get there, right? If I how many ways can you draw a square? If I specify the length of the square, there is only one way you can draw a square. Let's say draw a square of 1 centimeter. I mean, yeah, of course you could say I could draw it using a pen, using a pencil, using black ink, using red ink. But let's for a moment, if we forget about that, there is only, if I fix the size of the square, the length of the square, a square is like, it's ordered in the sense that there is only one way to draw a square. But if I say that just scribble on the paper, the only constraint being the total length of your, like let's say you start with your pen from here and you draw some scribbles, like random scribbles, not any particular geometric shape. The length of your pen ink, that this entire trajectory, the length should be, let's say, 2 meters. This is the only constraint. Now there are many ways you could do this, because I have not constrained that it has to be a square or triangle or like this or like that. Just 2 meters. So you start here, you can go this, you can go that, you can do this, like you can do many ways as long as you stop at 2 meters. That's it. So entropy is more, and which is more disordered, a perfectly beautiful ordered square or this kind of random scribbles? Of course the second one. So you see the analogy. But the point is, what is ensemble average and what is time average? Let's come back to the box of gas. You have fixed your energy, that's your macrostate. Now you want to measure something. Let's say you want to measure the pressure of the gas. It's a very, like it's an observable which you want to measure the pressure, just as an example. So time average means, of course, since there are the macrostate is fixed, that you have fixed the energy, but there are many possible microstates, and of course the system of gas is evolving. If you put some gas particles in a box, then particles will move among themselves. Yeah, there is no energy exchange with the outside, with the surroundings, but within the box the particles are moving about, colliding and doing all sorts of things. They're at equilibrium, but it's a dynamic equilibrium. They are not at, like, the particles are not fixed because it's gas, it's free to move, and there are not like strong bonds as in solids between the atoms. So yeah, and now you want to measure the pressure. So because everything is changing, let's say you measure the pressure right now and you measure it after 2 seconds or after 2 minutes, whatever, you may get slightly different values, of course, because everything is changing. Like I said, only thing that is fixed is energy, and that's why you're not measuring the energy. Well, if you energy is a macrostate that you already know, you have fixed the energy. So if you want to measure the energy, well, you already know, that is your constraint, that is given to you, you know the energy of the system, then there is no point in saying I want to measure the energy. If you want to measure the energy, then you define the macrostate by fixing something, some other variable. But you want to measure the pressure, and due to this variability, to get an accurate result, you have to take averages. So let's say you measure the pressure now, and after some time, and you do this millions of times. Like, yeah, ideally you do this infinite number of times, although that's not possible in reality. But you basically measured this pressure of the same system without disturbing the system a large number of times at regular time intervals. Because if you don't do it at regular intervals, then let's say I measure this now, I measure it after 1 minute, again after 1 minute, again after 1 minute, but then I measure after 2 minutes. So there is some bias I'm introducing in the average. So average should be taken at regular intervals. So you keep measuring this for a large number of times at regular intervals, and you get many different values. You divide them by the number of times you have measured, and you get an average value. This is your time average, because you're measuring at different times on the same system. Now let's talk about ensemble average. Ensemble average means, well, time is fixed here. So at one given point of time, you consider the box, you have the box of gas, and you consider there are a large number of, I mean, ideally there are infinite copies of the same box. Now, this is not possible in practice, of course. You have a box of gas, so that's why in real life, in experiments, you use the time average. That's why we plot the time series and that kind of. So we use the time average in experiments, because if you're actually doing an experiment, you cannot create up to 1 billion copies of the same box of gas, but you can take measurements for a long time. But this is a statistic in statistical physics, for at least in theory, this is a very important tool, important concept, the ensemble average. That's what I'm discussing, and you will see why in a moment. So ensemble average simply means that you take the box and you just, hypothetically consider an ensemble of such boxes, which means a large number of copies of some box. And when I say copy, I mean identical copies. By that, the macrostate is the same. So all of these copies have the same macrostate, the same energy, but microscopically they can be different, because, like I said, different macrostates can correspond to the same macrostate. Because again, if everything was exactly the same, then there is no point in creating copies and taking average, because you'll get back the same value. So if you know the value is going to be 5, you won't measure it 5 times and say that yeah, I measured 5 times and I got 5, because of course I know I will get 5. So it's 5 plus 5 plus 5 plus 5 plus 5 divided by 5, so it's 25 over 5, it's 5. Nobody does that. So values can fluctuate because the microstates are different. Now according to ergodic, so you have the ensemble, you have many copies in space, and at one given instant in time you take a snapshot of all the copies and all the values from each copy and you take their average. So this is their ensemble average. So you see, now ergodic hypothesis says that if the system is in equilibrium, then the ensemble average and the time average, they have to be equal. Yeah, what's the big deal? That's what we would have expected anyway. So it doesn't matter whether you're measuring like large number of times, I mean at irregular intervals of times and averaging it, or you're measuring and hypothetically creating copies. So yeah, that makes sense in a way. That's the ergodic hypothesis. So what's so special about it? What does it prove? What does it mean? I know what you're thinking. Well, this is important because let me come to the second statement of the ergodic hypothesis now, which says that in your, let's say you have many possible microstates, the system can explore many possible microstates. I simply mean that, okay, my constraint is fixed, that I have energy E. Let's say I am the box of gas, inside me are many gas particles. So as long as I respect the constraint, the macroscopic constraint at the fixed energy, I can explore many different microstates. I can say, okay, this particular microscopic configuration respects the constraint, so this gives me energy E. Let me slightly change these particles here and there. Okay, I still have energy E. Let me explore some more configurations, and it will keep doing this. And the more it will keep doing this, what it's actually doing is that it's traveling through the configuration space. You know, it's moving through the configuration space or the phase space. It's a mathematical construct. Now I don't want to talk about the phase space in this video because either you already know it, or if you don't, then I have made some previous videos about this. In this video it will, like, then this would be, it's already 11 minutes. I don't want to go into the phase space. That really deserves a video of its own, Liouville's theorem, phase space and all that stuff. But the point is that, so yeah, this system is exploring many different configurations, and if a system is ergodic, then in theory, I mean in principle, it's possible for the system to move from any configuration to any other configuration at, I mean, given enough time, basically. So now you can think, okay, that's a bit confusing statement. Like, how are these two statements equivalent? First one is easy to understand. Okay, time average is equal to ensemble average for a large system in equilibrium. Okay, that's fine. But what did you say was the second statement? Well, let me repeat and then I'll explain the equivalence. It says that, like I said, the system is exploring different configurations. Now, if the system is at equilibrium and if all the other conditions are met, so it's possible for the system to move from any configuration to any other configuration given enough time. So yeah, in theory, you could think of a very arbitrarily long amount of time as well, but it's still possible. It's not like, it's still reachable in a arbitrary amount of time. Like, actually, it cannot be an infinite amount of time. So you can reach any configuration from any other configuration in a finite amount of time, but the statement is actually you can reach arbitrarily close to a given configuration. So basically you are here and you want to reach here, so you can reach arbitrarily close to this place in a finite amount of time. And by arbitrarily close, I mean that in the phase space there is some uncertainty also, if you think about the quantum, like the position momentum uncertainty. So you can reach that state, like if you can reach arbitrarily close to that configuration, means you essentially you reach that configuration. These are just mathematical subtleties which are very important, by the way, but I don't want to go into these points in this video, by the way, because this is actually pretty confusing if we go deep into it, but also very important. So yeah, and why where is the equivalence? Because, well, if let's say this statement was not true, that means if there is at least one configuration that you cannot reach ever, you cannot reach in finite time, that means you cannot reach ever. That means when you are talking about the ensemble, you are creating the copies, so there is one configuration which will not be in the copy. I'm sorry, when you're talking about the ensemble, you create all possible, you create an infinite number of copies, so you have all the microstates there. You see what I'm saying? When you're creating an ensemble, but the very definition of an ensemble is that you create an infinite number of copies of the same system, the same macrostate, but for all different possible microstates. Since there's an infinite number of copies, all different microstates you have. So in the ensemble average, you will have the contribution from this configuration as well. But then we're saying that it's not possible to reach this configuration in finite time. If this statement is not true, we are trying to prove this by contradiction. That means in the time average, even though you are taking measurements for infinite amount of time, you will never reach one configuration which is there in the ensemble. So then these two averages will not be equal. That means if this statement is false, that statement is also false. This is not a rigorous mathematical derivation, but I think I showed you why these two statements are at least related. And that's the best I can do in a video verbally. Especially because I'm not assuming that all of you are expert in statistical physics, because this video is maybe very basic for some of you, but for some of you it might be a bit new terms and stuff. So that's why I want to keep it balanced and layman friendly basically. But again, the intuition is very simple actually. And we are also assuming something here, that is what you may think, that in equilibrium all the possible microstates are equally likely. That's what we call the postulate of equal probabilities, equal a priori probabilities, more exactly. So what I mean by that is that, let's say for a given macrostate you have, well, usually you can have an infinite number of macrostates, but just for example, let's say you have three possible microstates for a given macrostate. Just a simple example, just to keep things simple. So, and then the assumption would be that the probability of all the macrostates, the macrostate is fixed, it's given, the probability of all these three microstates would be equal. That means 1 by 3, 1 by 3, 1 by 3. This is the assumption which is always there when the system is at equilibrium. I keep saying this because if the system is not in equilibrium, of course there is some preference, there is some, you cannot say it's really ergodic, the system will be biased towards equilibrium, so it will move in like that. You cannot really assume these kind of arguments of non-equilibrium statistical physics. Well, that's where things get difficult. You need to talk about fluctuations, you need to talk about, for instance, the fluctuation dissipation theorem is a very important I won't say it's really like, but yeah, it's a good kind of gives an idea. But yeah, in non-equilibrium statistical physics, you need to talk about fluctuations. You need to talk about some very complicated situations like reciprocity, gradients, driving terms. Because usually when something is moving against the gradient, that means it's a classic non-equilibrium behavior in a way. It's an active process in a way, because you are in a way you are driving the system. At least locally you can drive the system away from equilibrium. That's really complicated, by the way, not the point of this video. But all of this we're talking about, this is the classic postulates of equilibrium statistical physics, the starting point basically, which is very important, by the way. Maybe not really as interesting as non-equilibrium, but works in many cases, really important, and it's the backbone. I mean, it's the groundwork, so you cannot ignore this. And yeah, so I mean to say, sorry, I kind of lost. Where was I? Yeah. So why does this assumption that all the probabilities are equal? Like I said, 1 by 3, 1 by 3, 1 by 3. Why is this assumption important, and how does it relate to ergodicity, ergodic hypothesis? Well, it's really not very difficult to see that, because if I assume that, well, out of these three possible microstates in our example, this one is more likely. So the probability of this is, let's say, 2 by 3, but the probability of this is 1 by 6, and this is also 1 by 6. So it's like, did I get it right? Because the sum of the probabilities has to be 1. Yeah, I think I got it right, because 1 by 6 plus 1 by 6 is 2 by 6, which is 1 by 3, and you have 2 by 3. So 2 by 3 plus 1 by 3 is 1. So the probability of one state is 2 by 3, the other two states are 1 by 6, 1 by 6. That means, of course, this state is being more favored. 2 by 3 means what? 4 by 6. And that's 1 by 6, that's 1 by 6. So this is a highly likely state. That means this assumption doesn't hold. Now the question is, how does this change the ergodic argument? Well, you think about it. When a state is more likely, the system is will be spending more time there. That means even if you're taking time measurements at equal intervals, you will take many measurements for that same microstate which has a higher probability, and less measurements for the others, because now they're being weighted by their probability. Same for the ensemble. I mean, the one which is really well. Let me just tell this in a slightly simpler way. These are just heuristic arguments, by the way, because the real mathematics of phase space is a bit more complicated, and whatever I'm saying, like mathematically, well, some mathematician or some advanced theoretical physicist who knows the philosophy of statistical physics, who don't use it as a tool only, but who actually know the mathematics very well, they would object to me, because I have actually, what I'm giving you is just a heuristic argument. There are many other, for instance, phase space is really a high dimensional space, and of course there is the argument that for very high dimensions the volume doesn't matter, you can talk about the surface, and then the argument that Gaussian, but okay, just to give you the idea without going into technical mathematics, the thing is that if you attach more probability to one particular microstate than the other microstate, that means if not all the microstates are not equally likely, some microstates are more likely than the others which are less likely, in that case, even if you like I said, the time average would not really reflect the ensemble average, because, or even in the ensemble average, if you take into account the probability, you will create, like, well, what I mean to say is that it actually depends on how you're looking at the system. So if you're looking at an ensemble average, that means in the ensemble this particular microstate occurs a bit more because it's more likely. Same in the time average. you are likely to measure this more number of times because the system will spend more time there. But the question is, does it really break ergodicity? That's a very subtle point, because the basic yeah, this is an assumption, because if you don't assume that the phase space is uniform, if you assume that in some configurations are more likely, then the system is going to spend more time there and the system is going to spend less time there. So there is clearly a dynamics in that's happening. The particle is kind of getting attracted to the more likely states, and well, even intuitively it doesn't really sound like equilibrium, so you can understand. And if we don't assume that the system is at equilibrium, well, these kind of arguments in general, they do not hold. I mean, I hope I gave you the idea. But yeah, the more important point about the postulate of equal a priori probabilities that I was thinking is that if you assume this postulate is true, this argument is a bit subtle and maybe not, I guess, not totally correct mathematically, but if you assume that all microstates are equally likely, and if you spend infinite, almost like an infinite amount of time, like measuring the particle, measuring the system, measuring your observable for an infinite number of times, so if that, what this means is that in a way you can think of it like this: the system will not visit any microstate twice, like more than once, without visiting all the microstate once, at least once. I'll give an example. Let's say you have a hotel with 10 rooms, and what do I mean by that the probability that there is, so let's say the probabilities are uniform, that means all the microstates are equally likely. So in our simplified example for the hotel case, this would mean that we would want all the rooms to be occupied by exactly one guest. So let's say there are 10 rooms and there are 10 guests, very simple, very like an ideal situation, perfect situation. You put each guest in like one guest per room and you have 10 rooms filled, uniform, it's fine. Now let's say, so this is what you would usually do, right? But now let's say you have 10 rooms, you want them to fill, but you have 10 guests, but you put 3 guests in one room, no guests in some rooms, and let's say one guest in, so you fill them like this, not uniformly. It's clearly not uniform. Now the point is, if you were to measure a system, some observable on a system an infinite number of times, and what you're getting by that, the time average, if that is turning out to be equal to the ensemble average, in the ensemble average you have all possible ensembles. What this means is that the system does not come back when you're measuring it in time. The system visits all the possible microstates exactly once, and it does not come back to a microstate it has already visited before visiting all the other remaining microstates at least once. So that means you can fill more than one people in a room only after all the 10 rooms are already filled. So there is one person in each room, everything is filled. Now if a 11th guest comes up, you have no more room, so you have to accommodate him to with one in a single room with a guest. That's it. But if there is an empty room, without filling it, you will not put 2 people in one room, right? So that is the thing I'm saying. And so again, like I'm saying, this is not really, this argument is a bit heuristic and also a bit subtle, so don't take it like, I'm not, just to give you the idea, this is like, don't take it like very from a, like, from the physics point of view, maybe slightly slightly incorrect technically, but you still get the idea. That's the point. But I gave you the disclaimer. So you are doing the time average. You are measuring all the all the microstates. You don't know what microstate you are measuring because the system is evolving in time. So you are letting the system decide whether it will spend time in one microstate more time or less time, or it will spend uniform time. That's because the system is evolving in time. You are not letting it decide. But if you measure at finite and regular intervals of time, infinite number of times, you get a time average which is equal to the ensemble average. And in ensemble average, it's in your hand, because you are saying that no, we have an infinite number of ensembles, and well, basically you can think of it like that we have all the ensembles exactly once, because in ensemble average you cannot have a microstate repeated just because it has a more likelihood probability. This is the point I kind of missed maybe in a few minutes back. But ensemble average means, let's say you have 3 possible ensembles, like I said, one with probability 2/3, one with probability 1/6, and then 1/6 again. But if you talk about the ensemble is just the collection of all possible microstates. So you will still have three microstates in your ensemble. Just because you have a higher probability for this 2/3 one, you won't have like, okay, let's have 4 copies of this microstate and 1 copy, because usually ensemble doesn't take that into account. But if you're measuring the time average, that means you are letting the system evolve. It's not in your hands. Now the system will want to spend more time in the microstate which has 2/3 probability as compared to 1/6. So if you measure the time average, you will get something which is a bit more biased towards the 2/3 microstate, and the values will not match basically. That means if the probabilities are not uniform, then this time average would not be equal to ensemble average. But ergodic hypothesis says it is equal in equilibrium. As the number of measurements and the system is large enough, there are infinite, both tends to infinite, so they're equal. So that's the thing. So this is kind of like always an assumption that we're talking about equal number of the each microstate is equally likely, because first of all, this is mainly because it's not really surprising. It's not a very foolish or stupid assumption to make, because we are saying that all of this is true at equilibrium, and when a system is at equilibrium, that means that all the microstates are equally likely, because if something is more likely, the system would want to go there, then again there will be a force. It's not really in equilibrium, and once it's in equilibrium, that means all of that has already happened and the system has settled in a state when all the probabilities are equally likely. So the system will keep exploring the configuration space. There will be many possible microstates. It will keep evolving, but in equilibrium. So that's the point of the ergodic hypothesis. Now, one last kind of good this is the beautiful analogy I want to discuss with you guys in this video, is about the central limit theorem and normal distribution, basically the heart of statistics, random variables, and also the heart of statistical physics in a way. Well, so now again, I'm not assuming you're an expert, of course. So what I mean by the normal distribution is simply that, let's not get too much about a Gaussian integral, that kind of stuff. It's simply that it's a bell-shaped curve. You must have seen this kind of distribution, like it's a bell-shaped curve. Now, what are we plotting against what? I'll tell all of that to you in a very simple example, very common example also, by the way, so maybe you already know. Let's say you want to measure the height of all the people in the world. It's not really possible, but yeah, let's say. And you want to plot a distribution. So let's say this is the height in your vertical axis. So let's say in centimeters or in inches, I don't know. This is a very low height. This is a high height. So tall people, and these are the number of people. Wait, I'm sorry. Sorry, this is the height. Your x-axis is the height, and in the y-axis you have the number of people with that particular height. So this is a very small height, like almost zero. So well, no human has exactly zero height, so you start from zero. Now as you move in x-axis, let's say here it's a very small value of height. So well, the infants, the babies, the kids, or like a good portion of the population, not majority, but a good portion of the population has that height. So maybe it's somewhere here, because in the y-axis it's the number of people with that particular height. In the middle, somewhere, which is the average height, like the usual, not very tall, like not abnormally tall, but not abnormally short, then well, most people fall in that category, so it's the high number, so you're rising. But then again, if you move further, those are the abnormally high. So, well, most people are not like, let's say 7 foot or 8 foot tall, so you start decreasing. So the thing is that all the heights of all the humans on earth, first of all, there are a large number of humans on earth, so it satisfies the constraint that the system must have a large number of particles or whatever, in this case humans. That constraint is satisfied, and also they're independent, because well, not really, but to our first approximation, maybe yes, to some extent you can assume them, because well, my height really is independent of your height, but not really, because not really true for all humans, because my height is in a way genetically affected or correlated with the genetics with my parents' heights and that kind of stuff. But yeah, on average we could say maybe independent to a good. So basically, when you have what the central limit theorem says is that, and this is the heart of the, like I should say, the normal distribution or the Gaussian distribution, this thing, the bell-shaped curve, is that if you have a random variable, so in this case the random variable was the height. It was random because well, you cannot predict the height of the people. If you know the height of the first 10 people, you cannot predict what will be the height of the 11th people. So that's why it's a random variable, right? So if you have a large number of random variables, this is a theorem basically. It's a mathematical theorem. It's proven. So they would always tend toward this kind of distribution, that first they would start from a small value, they would increase, and they would again decrease and fall back to zero, and that the highest value, that is the most likely value, which is the mean in some cases, not in all cases, by the way. Statistics is a bit more complicated. The mean, the average, and the most likely value, these two, like, they're not always the same, but yeah, this is the peak. This is the most likely value. The highest number of individuals have this value, and there is a spread, which means this distribution width in a way, because if it's a distribution which is like this, so well, it's very random, it's very uncertain, because yeah, this is the highest value, but it's just slightly high. I mean, it's just like this kind of thing. It's a hill, but not very high, and it's widely spread out. So even when you are far from the most likely value, you do have some decent probability. But if you have a peak like this, like a very narrow kind of peak like this, so that means this is the maximum, like the most likely value, and the fluctuations or the standard deviations from the mean, they are only slightly. So the other values, they're only slightly around the mean, but yeah, if you go far from the mean, you are at zero. So it's a very certain, very specific distribution. Like you don't have a lot of randomness here. That's what I'm saying. But yeah, both of them follow the same mathematics, this kind of bell-shaped curve. This width, the height, all of this depends on the parameters, like the mean and the sigma, the standard deviation. But that's what I mean. They follow the same mathematical expression. You can get it from a Gaussian integral. So the central limit theorem, or even the law of large number, it says that if the number of particles or even the number of measurements you are having tends to infinite, you will always get back this distribution for any random variable, independent random variables. Yeah, the condition being that the variables have to be independent and identically distributed. By identically distributed, like in a way you could think of what I was saying about probability, like uniform probability, no particular thing being preferred in a way. So when you're measuring the heights of the individuals, you will not prefer one particular individual in any, like there shouldn't be any such bias. And also independence, like I told you. So independence simply means no correlation between the two, in a way. Now the point is, what I'm saying is that, well, if you think about it, what I'm really saying is that, how do I put it? I would like to give you two examples, very simple examples. Before that, another small, like maybe a small example. So if you toss a coin, you get either a head or a tail. So if you toss a coin, you know that theoretically the probability of getting a head is 50%, getting a tail is 50% again. So even if you toss a coin 1,000 times and you get a head 1,000 times, even in the next throw, the probability still remains 50-50. You won't say that we have been getting so many heads, so the probability of tail maybe should be a bit more than 50%. That kind of argument doesn't hold. Because why? Because each trial is independent. But at the same time, let's say you toss a coin 10 times and you get 8 heads and 2 tails. So of course you don't conclude that the probability of getting a head is 80% and 20% is the probability of getting a tail. No, because because your number of trials is only 10 times, which is a very small number. Now let's say if you toss a coin 100 times, you can still get 80 heads and 20 tails, but it's a bit less likely. You are more likely to get maybe 60 heads and 40 tails or something like that, or maybe 40 heads and 60 tails. What I'm saying is that this the boundary is closer to 50%. Because now we're at 60-40 and previously we were at 8 and 10. 8 and 2, that's 80%, 20%. If you toss a coin, let's say 1 lakh times, it's very likely that you are somewhere nearly 50,000 times, around 50,000 times head and around 50,000 times tail. Not exactly. Now, if you toss a coin infinite number of times, in theory, in that limit, in that asymptotic limit, well, you are expected to have exactly 50% head and 50% tails. So this is what you can say in a way is the law of large numbers, which says that as the number of trials goes to infinite, then your measurement probabilities, they actually converge to the theoretical values. And it also shows you that, well, it's kind of like an averaging effect at play. Theoretically, for each independent trial, the probability is always 50-50. You cannot change that. Your experimental results doesn't change that fact. That's theory, that's established. But when you're getting this matters because, like I said, law of large numbers. So you need a many number of trials to decorrelate the system. In a way, this is a bit physics language, because when you're tossing a coin, it's not really, decorrelate is not really the thing. But in physics language, as the system evolves, it decorrelates from its past memories. True for humans also. I mean, with time you forget your memories. But in physics, what I mean that if the system is starting in a very particular specific initial configuration, it will evolve in a way which will be biased toward that configuration, because there will be some memory, some correlating effect that, okay, I started in that configuration, so I have to carry that weight. So I cannot really evolve that way because that will violate that kind of thing. But after a very long amount of time, so after many independent, like kind of, exploration of configuration system, the system more or less is in equilibrium. It is equilibrated, and right now it has no memory of that particular configuration. Right now all the configurations are equally likely. What we discussed, the postulate of equal probabilities. Now, how to get an intuition for this bell-shaped curve? Because statistical physics is actually all about, at least in equilibrium statistical physics, it's all about the Gaussian distribution. It gives you the mean, it gives you the variance, like how much you vary from the mean, the standard deviation, and these are the two parameters you need to characterize the Gaussian function. And this is good because in statistics, for instance, if you look at the mathematics, the moment generating function, the cumulant generating function, you have those kind of stuff, the generating functions. The thing about this is that if you calculate the first and the second moment, you get the mean and the standard deviation. All the other moments are automatically come out to be 0 if you talk about averages. That's the thing. And that's why in statistical physics, we do talk about averages. That is why this condition is required, that we must have a large number of particles which are independent. Otherwise, if you have only 1 or 2 particles, you cannot really talk about averages in that sense, right? Then it would not be really accurate. So that's why we talk about averages in statistical physics. And statistical physics works because for averages, these kind of generating functions, they give you a Gaussian distribution, which is pretty, cool. Because once you can characterize the mean and the sigma, the standard deviation, you have all you need to construct the Gaussian distribution. Now, the last part of the video, I would just give you two very simple examples to kind of show you this where this give you a visual intuition of where this Gaussian, like this bell-shaped curve comes from. This is of course true only for an unbiased kind of thing. Otherwise, you have many different kinds of probability distributions. Poisson distribution, if it's a directed process, if the probability of success is very small, then you have a kind of shifted, it's not really a symmetric bell, because this bell-shaped curve, Gaussian I'm talking about, it's symmetric. So if you, this is the highest point, this line, so it's symmetric about both these things. But there are other kinds of distribution, like for instance the Poisson distribution, which is not symmetric at all. You can have many other kinds of distributions. These are like special, you can also derive that from the Bernoulli distribution for if you have an event where like you have either a success or a failure. Anyway, point is we will discuss two examples. One is that, well, actually we'll discuss one example because the second example is pretty common. You should, and well, I'll just mention it briefly. So if you start with like the discussion I already gave you, the argument I already gave you, we start with that you have a random variable and you are performing measurements of that random variable, and as the number of measurements will go to infinite, then you get this kind of bell-shaped curve. If you have one measurement, well, you don't get this average bell-shaped curve. Of course you don't, because you have just one measurement, just have a value. But if you do this many number of times, you ideally, as the number of measurements goes to infinite, you have this bell-shaped curve. So this is, I'm not going deep into this. This is the usual argument, the way it is taught, and that's good because this shows you the idea of time average. But now I would like to give you a similar but a slightly like, this is not exactly like, I'm not saying this is exactly, but like again this is a heuristic argument, but you can intuitively try to think about it in a very good way, very intuitive way also. Let's say you have a die, you have a single die. Right now we are focusing on, you could say, I won't use the word ensemble because we will be changing the observable, as you will see. But right now we're focusing on an infinite number of particles rather than an infinite number of measurements of the same system in time. Slightly different. But think about it, this difference is subtle, by the way. It's not really ensemble average, as it should be clear to you once I tell. So let me begin. Let's say you have a single die and you roll the die. So there are 6 possible outcomes with equal probabilities, right? 1 by 6, 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 1 by 6 for 1, 2, 3, 4, 5, 6. So if you want to plot the distribution of the outcome you get by rolling a single die, this is the probability and this is your possible outcome. So you have 1, 2, 3, 4, 5, 6. For all the cases you have probability 1 over 6, so it's just a straight line at 1 over 6, at the probability equals 1 over 6. It's a constant probability. You don't have any bell shaped or anything, it's right. Now let's say you bring 2 die into the picture, but this is why I'm saying this is not a really perfect example because we are changing the observable. It's not, but this is just to give you the intuition. If you bring 2 die into the picture, well, right now your observable, let's say, is the sum of the outcomes. Previously it was just the outcome you get by rolling a die. Right now it's the sum of the outcomes on both the die, so you roll them simultaneously. So what can you get? Can you get 1? Well, no, because you are rolling 2 dice, and even if I take the minimum values in both cases, that both the dice show 1, then my minimum outcome is 1 plus 1 is 2. The maximum similarly is 12, of course, because if both are 6, you get 12. And in the middle you can have 3, you can have 4, and so basically from 2 to 12 all the numbers are possible. So on the x-axis you have 2, 3, 4, 5. Let's say you start from 1, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. For 1 the probability is 0 because you cannot have the outcome 1 if you're observable, if you're measuring the probability of the of getting a number. I mean, if your observable is like the sum of the 2 outcomes, then the probability of getting a 1 is 0. So start from 0. The probability of getting a 2 is only 1 because both the dice must show 1. In no other combination of outcomes can you get 2. So it's just 1. So it's slightly increased. Probability of getting a 3, well, you can get 1 on the left die and 2 on the second die. You can get 2 on the first die and 1 on the second die. In both these cases the sum is 2 plus 1 or 1 plus 2 is 3. So there are 2 possibilities. It's slightly increased. For 3, okay, for 4. Well, for 4 there are many possibilities. You can get 3 1, you can get 1 3, you can get 2 2. Well, 2 2 is basically the same thing because, well, but still you get 3 possibilities, increased a bit more. For 5, well, you can get 4 1 or 1 4, you can get 3 2 or 2 3. I think that's it, but down there are 4 possibilities. For 6 you can get 3 3, which is just one case, by the way, because it's the same thing even if you flip. You can get 4 2 2 4. You can get 5 1 1 5. So 4 and 5 possibilities. Yeah, 5 possibilities. Still increased a bit. For 7, now let's think about 7. Well, You can get 1661, that's good. You can get 2552, that's good. You can get 3443, that's good. Well, you already have 6 possibilities, and you can get 2 3 4 4 3. If you want to go to 2, well, again you end up with 2 5. But again, so maybe I'm missing out some possibilities. I'm not doing this on pen and paper, but you see the idea, it's increasing. But now let's move to 8. Okay, for 7 we already identified 6 possibilities. Let's see where this goes. For 8, you can have 6 2, you can have 2 6. You have 2 dice, by the way. Is there any other possibility? Well, yeah, of course. You can have 5 3, you can have 3 5. Is there any other possibility? You can have 4 4. You can, yeah. Is there any other possibility? No, there isn't. If you go to 3, then again you have already considered 3 5, right? So you have we identified 6 possibilities. Right now we have 5 possibilities, because 4 4, 3 5 5 3, and 6 2 2 6. See, it kind of from starting from 0 at 1, it is rising up to 7, then it's decreasing. 8 for 9 10, and similarly for 11, the number of possibilities is really less, because you can have 11 only if you have a 5 6 or a 6 5. Think about it. In no other case will the sum give you 11, right? For 12 we have only one possibility. Again, it's 6 6, both 6 on both the dice. Otherwise you're never going to get a 12. For 13, again, it drops back to 0. You have no possibility of getting a 13 if you have 2 dice and you are measuring the sum of the 2 outcomes. If it can never be 13. So you see, you don't have a bell-shaped curve yet, but you see this straight line changed to a triangle, increasing and then decreasing. Add a third die. This is a bit, of course I'm not going to discuss in the video, but you can try it out if you have time or if you feel like it. Add a third die, and now if your outcome is, what numbers you will get from, like the sum of the outcomes of the 3 die, it will get slightly smoother. I'm not saying you will get exactly the bell-shaped curve, but you'll get this similar kind of course it will increase then decrease, but now you have many more possibilities, of course, because if you have 3 dice, the minimum value is 3 and the maximum value is 6 times 3 is 24, so 3 to 24. And if you keep doing this, adding more and more die, well, this is not really a perfect example, because first of all this is also expanding, you are stretching it. If you have 10 dice, well, your minimum value is 10, your maximum value is 600 actually. 60, not 600, 60. But so you have gone from 1 to 6 to 10 to 60. But in a way, you're just scaling it up. You see what I'm saying? 1 to 6, 2 to 12. So just multiply by 2, the first and last value. 1 to 6, you multiply 1 by 2. Not really, because you have 2. But you multiply 6 by 2, you have 12. Then you have, for instance, for 10, you have 10 to 60. So you start from the number of die you have, because 1 is the minimum, and the last value is given by the, basically, you see what I mean. So in a way, you can think of it like you're scaling it, but at the same time you're stretching this, but you will get this smoother and smoother kind of I should say curve. You will be approaching this bell-shaped curve almost if you have an infinite number of die, or a large number of die, and at the same time the probability is also increasing. Because in the case of the 2 die, for instance, there were, I think, 6 ways to get 7, right? But if I have 3 dice or like more number of dice, I think there are more number of ways to get the intermediate number. Not 7 in this case, but the intermediate number. So that's also true. You're not just going this, you're also moving up. So well, I think that's just something to think about, because like I kept claiming throughout the video, these are like heuristic arguments, and this is not really true on all accounts, because for instance, here we are even talking about an observable, which is here it's a bit different. We're talking about, we are adding more and more die, but that's not exactly the same thing conceptually as the ensemble average. But I think you get the idea what I'm talking, and it's something really important that you can think about, that how we can intuitively think about why in general independent and identically distributed random variables naturally tend towards this normal distribution. There is a mathematical proof, by the way. It's very difficult. It's a bit like but you get the intuition even by these simple examples, and there are many more such examples I could go on, but this is a really subtle and important point. I really kind of encourage you to delve more into it. There are lots of better YouTube videos that show all this stuff with animations and stuff, better resources on the internet, so have fun exploring. Thank you for watching.